Today, we have massive innovation happening in the field of artificial intelligence, and new capabilities are emerging every day in terms of what's possible. The infrastructure behind these advancements of AI is driven by solutions that are very good at collecting, labeling, training with a combination of real-world and synthetic data to deploy robust machine learning models that increasingly automate more and more complex tasks. Organizations that are capitalizing this resource have an unfair advantage to deliver better products and experiences to their customers. One field that is pushing the boundaries is the automotive sector. Millions of vehicles are being produced with machine learning models to translate raw sensor data into actionable intelligence in real time. The models that make this happen require dedicated hardware in the vehicle and robust training infrastructure in the cloud. The vehicles themselves are being retrofitted with sensors such as cameras, radars, or even LiDAR for vision, and GPS and inertial measurement units for positioning. Advanced sensor fusion algorithms combine this data from multiple modalities to create a complete 360 picture. As each vehicle learns to interpret its environment, it is capable of becoming a probe which can share what it learns about the environment into a centralized cloud infrastructure. Vehicles being driven in the field can record events, such as disengagements or interesting scenarios they haven't seen before. These corner cases give a more holistic perspective on the realistic driving behaviors. The developers working on the technology within car manufacturers can then backhaul this recorded data to capture the scenario in simulation. This scenario is either played back or rendered in a game engine for more flexibility. In order to render the models in the game, the recorded dataset needs to be ground truthed, where the objects in the scene are correctly identified. Errors in the trajectory or the detection and classification of objects needs to be corrected. At Hyperspec, we enable developers to request for these interesting scenarios from an active fleet of vehicles equipped with advanced driver assistance technology. By collecting data when interesting things happen, we can create a new scenario that can diversify the library of scenarios used for the machine learning pipeline. This diversification makes the models more robust and performant in real-world conditions. Through intelligent data collection, the overall performance of the AI can be boosted. This surgical precision improves the operational efficiency and the development cadence. Being a startup, we also maintain a core library of scenarios to enable our customers to utilize our boilerplate machine learning models. This is useful if they need a place to get started. We can even dispatch a data collection mission to create scenarios on demand. Our instrumented vehicles are equipped with cameras, radars, LiDARs, and other inertial sensors. These sensors allow us to capture high-fidelity data sets that are ideal for ground truthing. If need be, we can also assist our customers in retrofitting their own vehicles. We also have a portable mapping kit that can be carried by hand. This is useful for connecting indoor spaces with outdoor environments. Our aerial-to-ground fusion algorithms also allow us to correct localization drift in previously collected datasets. This is great if you already have sensor data that has been collected, but the data is erroneous. Using vision positioning, we can boost the accuracy of the previously collected trajectories without requiring any additional hardware or any additional data collections. For areas that have long gaps in aerial coverage, our SLAM algorithms provide reliable dead reckoning pose estimations with minimal drift. This is useful if you need to drive in GPS-denied environments while still maintaining positional accuracy. In the cloud, our ground truthing pipeline automatically corrects errors and makes the scene self-consistent. This can be used for correcting localization error or even sensor calibration. This is done without additional hardware. We can use any object in the aerial image as a feature for localization on the ground. Our tools can quickly create features and make that information available to the camera or the LiDAR sensor. Our object detection pipeline is also able to parse 80 different object classes while running at 15 frames per second. The models themselves can be tuned for both the distortion-free lens or a heavily distorted 360 equirectangular image. The stitching process creates a seamless 360 perspective, which we can utilize to process the information in the scene. The object labels themselves can be cross-referenced in the ground truthing pipeline to rectify any mislabeled objects. Our MLOps pipeline allows developers to analyze the annotations frame by frame to retrain and deploy new machine learning models with ease. Additionally, our usage of unsupervised machine learning and self-supervised techniques dramatically reduce labeling time and the cost of human resources. In summary, the integration of machine learning and machine learning operations in the development of ADAS systems can significantly enhance the speed, accuracy, and performance of the systems while enabling cost-effective solutions. Automotive manufacturers can take advantage of these technologies, and they'll be well positioned to compete in the market and offer safer and more advanced vehicles to their customers. As Hyperspec grows as a company, I hope you can join us on the journey and help deliver a safer, more accessible future that democratizes transportation. Thank you.